This is the brief on classifying linear differential operators using the behavior of their principal symbol. So, we're going to look at this really fundamental link between some key equations in math. These are the linear differential operators, or LDOs, and how one single tool, the principal symbol, actually tells us everything about their physical behavior. First up, let's just pinpoint what these operators are. You've probably heard of them: the wave operator, the diffusion operator, and the Laplace operator, right? These are all famous LDOs, and they're basically the math that describes how things move, spread out, or just stay put. Second, the principal symbol is like the ultimate sorting hat for these equations. I mean, the whole classification, whether we call an equation hyperbolic, parabolic, or elliptic, it all comes down to the zero set of this symbol. You can think of this zero set as defining the characteristic directions, which are literally the paths that information is allowed to travel along. And finally, this is where it gets really cool, because these directions connect directly to what we see in the real world. For hyperbolic equations, like waves, you get two clear paths. That's why waves propagate so cleanly. For parabolic equations, think diffusion. You get one repeated direction, which leads to that classic instantaneous spreading behavior. And elliptic equations, they have basically no real directions, which means their solutions are all about a steady state, totally determined by the boundaries. So yeah, the principal symbol zero set isn't just abstract math. It's the essential map for understanding how these equations govern waves, diffusion, and steady states.